Like no one ever was. 7.2 transformations. Today we're going to take a graph and move it around. We've done this before, so it might not be completely new to you guys. All right, so here we have an exponential equation, y equals 2 to the x power. Remember, all of our exponents are going to be the variable now. All right, let's go ahead and graph that. You can graph it on your graphing calculator. You can graph it on Desmos, your choice. Here's what it looks like. It's kind of like the beginning of a roller coaster where it starts to go and then it shoots up really fast. Okay, so that's what our parent graph is going to look like. Let's see what happens to that graph if we put a negative in front of it. What do you think? What's a good guess? Here's what it looks like. It's in green. It now goes down. So the way you say that is that our graph is reflected across the y-axis. So it's reflected across the y-axis. All right. How about what if I put, instead of a negative in the front, what if I put a number in the front, like a 7? What do you think that 7 does? Here's what the graph will look like. It's in green as well. It kind of looks like it moves to the left a little bit, but actually what happens is it's vertically stretched. So we've done that with quadratic equations as well. When we put a coefficient in the very front that's bigger than 1, it actually vertically stretches it. So if you took the red line and you took it and you stretched it vertically, you actually have the green line. All right, so when you add a coefficient that's bigger than 1 in the front, you actually stretch it by a factor of 7. What if I put a fraction in front of it that's less than 1? So between 0 and 1, what do you think that does? Here's what the graph looks like. It's in blue now. Now it looks like it just scoots to the right a few, but actually what happens is we took it and we squished it. So if we took our red line and we squished it, vertically compress it, that's what the graph does. All right, so when you put a fraction that is between 0 and 1 in the front, it vertically compresses it. It kind of squishes the graph down. What happens if I take the parent graph and then I add a 7 at the very end? What do you think? A plus 7 at the end. It could be actually a plus 7 in the front too. It doesn't matter where you put the plus. It's a black line now. What happens? It actually is shifted up 7 units. So that is a vertical shift. If you were to subtract 7, it actually would shift it down 7 units. So that's a vertical shift up and down. Ooh, let's look at the exponent. What happens when you play with the exponent? What if I make the exponent negative? I wonder what's going to happen there. There's what it looks like. It's in black. The red is always the original one. All right, so what happens? It is reflected across the y-axis. So it just flips across the y-axis when the negative is in the exponent. So I want you guys to know the difference. Negative in the very front is reflection across the x-axis. The negative in the exponent is a reflection across the y-axis. So know the difference, please. What happens if I add or subtract to the exponent? What do you think happens? Let's see the graph. It looks like it shifted left 4 units. So a plus 5 shifts it to the left, and a plus 4 shifts it to the left, and if you have a minus 4, it actually shifts it to the right. All right, so we have a horizontal shift. If it's in the exponent, it moves left or right. If it's not in the exponent, it moves up or down. All right, so that's how transformation works. All right, just know that each part of the equation does something different, and you have to memorize all those parts. Next thing we have is Euler's number. I know it looks like Euler or Euler or Euler, but the pronunciation is Euler's, kind of like an oil rig. Euler's number is a fancy E. It's a constant number. It's the same as pi. You know how pi is like 3.14159 and it goes on forever? Well, E, Euler's number, is also a number and it goes on forever. If you find it on your calculator and push it, it's approximately 2.71828, and then this also goes on forever. All right, so it's a special number that will help us solve equations with x's in the exponent. All right, so you don't have to memorize Euler's number, you just have to know where it is on your calculator. Boom. There's actually two places that it's on the calculator. One place is above the division sign, and then one place is next to the left of the number 4. All right, and so know where that is, because you're going to have to use it for this equation. Compounded continuously. So yesterday we did an equation, or I gave you a formula for when you put like money in the bank and then you want to save up and see how much it grows. That's one way to do it. So where that equation was, I don't know, remember we put in $1,000 and it was 5% interest, and then so you calculate that number and you get more at the end of the year. And then next year you calculate that new number and then you see how much more you get after that year. And then it does it year after year. But this formula does it continuously, so it doesn't wait a whole year before it calculates your money. It's theoretically calculating your interest infinitely many times. And so let's see what this formula, the letters in the formula represent. The A is still the end amount. The P is the principal amount, the original amount you have. The E is Euler's number. And then raised to the R power, which is the rate. Remember that has to be in decimals. And then the T is just the time, how long it takes. All right, so let's go ahead and do one example. It is actually the same exact example as what we did yesterday. You have $1,000 in the bank, and the bank gives you 5% interest. But this time, instead of using the old formula where they calculate it every year, they're going to use this new formula because you want it to compound continuously. All right, how much money will you have after 6 years? Let's plug everything in that we know. The principal amount is still $1,000. There's Euler's number, and then the interest rate is 5%. Change it to decimal, 0.05, and then 6 years. And then again, you have to remember PEMDAS, order of operations. We have to do parentheses first, which is in the exponent. So multiply the two exponents together. 0.05 times 6 is 0.3. The next thing we do is we calculate e to the 0.3 power. Go ahead and do that on your calculator right now. Play around with the calculator key. Some of you guys might not be able to, you might not know how to do the little e to the x on your calculator. You have to use the second button or the shift button. But if you do it correctly, you should get approximately 1.3499. And then the very last thing you're going to do is multiply it by that 1,000. And you actually end up with $1,349.86. All right, so you use this formula if I asked you to compound continuously. You would use the old formula if you were asked to compound it annually. All right, that's all we got. Go ahead and try the homework.